introduce the speaker. We're very happy to have Hamsa Padmanabhan here with us today. Hamsa is has a wide breadth of research expertise, ranging from theory of in theoretical investigations in relativity and QFT, and also data intensive observational astronomy, astrophysics, and cosmology. She is currently a scientific collaborator and principal investigator of the Swiss National Science Foundation's Ambizioni grant at the University of Geneva in Switzerland. And previously, she was a CETA fellow at the CETA, the Canadian Institute of Theoretical Astrophysics in Toronto, and also before that, Tomala postdoctoral fellow at ETH Zurich. She graduated with a PhD in physics from Ayuka in 2015. And she'll be talking to us today about a multi-messenger view into the cosmic dawn. So thanks, Hamza, for accepting our invitation to talk here. And
Okay, can everyone hear me?
yes,
Yeah,
I can hear
great.
you.
So, okay, thanks a lot, Aditya, for the very kind introduction, and thanks for everything related to the organization of this. I do hope I can meet you all in person, hopefully sometime over the next year, assuming things go well. And thanks also to Ajit for the kind invitation so many months ago. What I'd like to share with you today is a bunch of themes which are interconnected and can provide us probably a very fascinating outlook into what is known as the cosmic dawn, the period when the first stars and galaxies lit up our universe. And interestingly, what is now very evident from data and observations is that looking at the period between this epoch and today offers really interesting insights into not just astrophysics and cosmology, but has the potential also to constrain theories of gravity and fundamental physics when the data is combined in the so-called multi-messenger way. So, to start with a very broad introduction to what we're going to be talking about, probably everyone in this room is familiar with the left panel of this slide, which is just telling you how bizarre our universe is. 95% of it is in a form which we do not understand, the dark matter and dark energy. And we are not really familiar with in day-to-day interactions. However, the ones which we are familiar with, and importantly, which can give us clues to understand the remaining 95%, are these baryonic or normal material. Uh, Interestingly, if this picture is sort of depressing or humbling, depending on the way that you would look at it, we're not even the only solar system, we're not only the only planet, we are not even made up of the most dominant component of the universe. However, if you look at the budget of how the material which we know and understand is distributed, this picture is probably not so familiar to many of the people. It is something like it's something which is even more, if you want, depressing or humbling. What it tells you is that even among the normal material, if you do a budget, then the kind of stuff which we associate as baryons are mostly the things in stars, planets, and so on. And these have always been, and even today, are less than 10% of even the baryonic material. The rest of it is and has always been in the form of gas in different forms. For example, there are some in the form of the neutral gas, something known as Lyman alpha forest between galaxies. There are some controversial arguments like whether some of them are like warm, hot in the intergalactic medium, and so on, at very high temperatures, emitting in the X rays. So, most of the baryonic material in our universe has been in the form of these kind of gas. So, understanding the cosmology and astrophysics through the only probe we have at the moment, which is baryons, involves a study of how this gas and these molecules and atoms evolved across cosmic time. So if we think about it, the gas you basically had just two salient transitions. The first one, which we're familiar with, is the recombination, and it occurred when the universe was around 300,000 years old. It led to the decoupling of the cosmic microwave background, and it ushered in a period which is known as the dark ages of the universe. So, dark ages because the material, like the atoms and molecules, were mostly neutral. The stars had not formed yet. And so you essentially had just the fading glow of the CMB, and there was no other source of light during this epoch. It lasted for about a few 100 million years, which is when the first stars and galaxies switched on. And this brought in this period, which is known sometimes as cosmic dawn, sometimes as cosmic renaissance, just to draw some parallels between Middle Ages and Renaissance, for example. And it sort of came to an end around about 1 billion years after the Big Bang, which is when it is believed that all the luminous matter, the galaxies and stars and other sources, completely ionized the existing neutral material back into protons and electrons. And today we see a highly re-ionized universe. So these two transitions are very exciting. And what is more exciting is that we can use these transitions and this timeline to answer some very key questions about astrophysics and cosmology. Depending on which epoch you are focused on, the kind of questions you ask and answer also evolve. So, the very local universe, like between today and the time when the reionization sort of completed, we mostly are focused on this question that can we use the intergalactic material, which is almost completely ionized, to constrain astrophysics and cosmology. So we can do surveys of individual systems and galaxies as well as the matter between them and extract constraints on the cosmology. Slightly further out, if we're looking at this transition itself, this epoch of reionization, we would really like to know what is the way forward to model this period, to constrain the evolution of reionization, and can we sort of garner some exciting theoretical insights from the formation of, say, the first stars, the first black holes. And as theoretical physicists, if we are really looking at also the very early epochs, we would definitely like to ask, can we use this wealth of information representing the data set which we are going to have in the coming decades, because it is closing the gap between the local universe surveys and CMB. So this richest observational data set could possibly be used to place pretty tight constraints on fundamental physics. So that would be the most ambitious question we can answer with the baryonic physics. So, in order to go through the evolution of the baryons, both during these reionization and the post reionization periods, a very recent development has been the formulation of a technique which is known as intensity mapping. So, in a nutshell, intensity mapping is very similar to what people have done for the cosmic microwave background, except that it is done in baryonic material. So, what is done is typically that instead of using a galaxy or an object by object survey, so which is like discrete tracers over the sky area, you make a map of the integrated radiation coming from that, that patch, say in the sky, without worrying about targeting individual systems. So this makes it much cheaper and more efficient to survey large volumes, large areas. And another advantage is that depending upon the kind of scale you are sensitive to in your intensity mapping, you will probe different kinds of tracers and potentially different astrophysics and cosmology. For example, at very large scales, it is hydrogen which is the most dominant between galaxies, and typically it is probed through its 21 centimeter spin flip transition. At smaller scales, you have a lot of star formation and other processes. And if you do intensity mapping with lines like carbon monoxide and the ionized carbon, which are good tracers of star formation, then you can get good constraints on the star formation history and its evolution. And needless to say, there are several efforts which are underway in the final stages of commissioning or even up and running to look at these baryons across these epochs in the universe, both with, let's say, hydrogen as well as with other lines like the molecular lines. We have, of course, the GMRT in India and the other experiments such as HERA, PAPER, LOFAR, etc., who are probing for the 21 centimeter transition of neutral hydrogen. And there are several such other experiments across the world. There are also experiments in the last two lines. I'm showing you some of them in the molecular gas and in the uh, ionized species, which probe the star formation rates in the smaller scales and also are complementing the efforts of the 21 centimeter. The very salient feature of doing cosmology with this intensity mapping technique is simply that it allows you access to potentially several thousand more modes than you would get with all the surveys which we have currently today. So for example, if you look at a 21 centimeter survey, it can close the gap between this and the CMB, and it can extend down to the gene scale of the material, which means that it potentially probes much smaller scales. And similarly, if you look at different frequencies in this transition, because it's a line transition, you are going to probe different epochs because of the redshift. And this is allowing you to do something like a tomography. So you can actually get, instead of a 2D surface, you can get a 3D image of the integrated evolution of what is happening between you and potentially up to the CMB. So in doing all this, there is something which we need to keep in mind when we are doing intensity mapping over these large volumes and across different redshifts, that this technique is prone to the interplay between astrophysics and cosmology. So what I mean is that when you look at, for example, the main observable, which you measure from an intensity map, it's called a power spectrum, and it's akin to the CMB temperature fluctuation power spectrum. So it's just these fluctuations in different scales. You don't have to worry about the detail of the equation, but just notice that this power spectrum contains contributions from the underlying cosmology, which is like, because it is tracing the dark matter in the large scale structure through the cosmology, but also it has an imprint of astrophysics in it, because you are really sensitive to the particular tracer. Like, for example, in this case, neutral hydrogen, H1, but it could be other tracers as well through, for example, here, their abundance. So abundance of the neutral hydrogen is something like the omega matter. It just tells you how abundant the hydrogen is across cosmic time, and their clustering as well. So in order to think about constraining cosmology and astrophysics, we really need to have a way to separate or model the astrophysics in a way which is kind of distinguishable from the underlying cosmology. So in order to efficiently do that, we found that a very natural technique happens to be using something which has been very successful in studying both the galaxy evolution as well as the parameters of the dark matter itself, the underlying dark matter, which is known as a halo model framework. So to introduce what this involves, it is essentially a way to combine the intensity mapping diffuse kind of observations with those in more traditional surveys, such as targeted galaxy surveys and individual objects. The way you would do this is to use two salient ingredients. The first is called the MH1. So here it's about neutral hydrogen, but this kind of completely generalizes to other tracers as well. It's measuring for you the average mass of the H1 associated with the dark matter halo of mass m and at redshift of z. And also, you'd like to know how this neutral hydrogen is distributed as a function of scale, as a function of distance from the halo, just the way you would do a distribution of the dark matter density itself as a function of scale. What can be shown, which we spent a couple of papers showing, is that when you take these two ingredients, you are able to model them in a way by which you can derive all the observables of the neutral hydrogen, both from intensity mapping as well as from discrete tracers. So I'll spend one slide on just telling you briefly how these two how these two main ingredients are connected to the observables. So the first one, the H1 mass to halo mass, typically has about 3 free parameters in it. So the first parameter is called alpha, and you would keep it as a up-down normalization parameter. It measures for you the fraction of neutral hydrogen relative to the cosmic fraction. So the cosmic fraction being this term here, which is a constant and depends on cosmology and helium and things like that. The second parameter, which is of interest, is known as beta, and it's called the slope. As you can see, it parameterizes the deviation from a proportionality between H1 mass and the halo mass. So were beta to be 0, this guy would be proportional to halo mass, and that's to generalize it to a non-unity slope, you would introduce a beta. Watch out for beta because it's going to become pretty important in the next few slides, and it has a physical meaning. The third parameter is called VC0, and VC0 is typically the parameter which controls what is known as the H1 boundary. In some sense, this parameter tells you what is the lower cutoff for halos to be able to host the neutral hydrogen. So if a halo is too small, this parameter will set for you that typically hydrogen is suppressed in these halos. This V is essentially a circular velocity rather than a halo mass, and it's very closely connected to halo mass itself. It is more natural to introduce this parameter in terms of a circular velocity. If you look at the profile is modeled almost identically to the way you would model dark matter profile. And it introduces something called a scale radius and a concentration parameter. The concentration parameter is inherited from dark matter, so you don't have to worry about this kind of exponent here. It just comes from the dark matter, and it's also very small. It doesn't do anything. The main parameters which are interesting here are the normalization of this concentration. So you would have something which sets a typical scale. So you need to know how that scale is changing, for example, also with redshift. So you'll put another parameter here which evolves it with redshift. For example, in the case of dark matter, this parameter would be set to unity. So these 5 parameters typically comprise for you the salient features in modeling the neutral hydrogen. And now we come to the data. So the data in neutral hydrogen.
Just
Yes.
one question that I had. Could you just explain again what the VC is? I'm not sure I understood it completely.
Yeah. So VC is the halo circular velocity. It is just square root of gm by r, where r is the virial radius. So if you take the way the halo mass is distributed, the VC0 will just scale with the m of the halo to the power of 1/3 and with redshift as well. So it's a circular velocity and it's directly connected to halo mass. It just sets a lower scale.
Okay, yeah, I guess I understood it right now. Thanks.
Great. So the data is quite diverse. As I said, there are data in the individual galaxies. So these are some examples of very comprehensive surveys which do like the 21 centimeter galaxy data between, at very low redshift. This is quite an optimistic bar. Most people would cut it off probably somewhere here. There's also data on the intensity mapping, which is coming from cross-correlating two surveys. It's been done right from 2010, and very recently we had cross-correlation. At higher redshift, it's very interesting to note that the salient data in the neutral gas is available from what are known as damped Lyman alpha systems. So these are the biggest reservoirs of neutral hydrogen which exist between, let's say, redshift of 1 and redshift of almost 5 to 6. And these are not measured in 21 centimeter line. These are measured in another line known as Lyman alpha line. We still do not have a full understanding what these systems are, but we know that they are the analogs of the highest neutral hydrogen bearing systems in the low redshift universe. I see a hand raised. Should we?
Yes, Mukesh, please go to your question.
Yeah, I have a question from the last slide.
Okay.
So you showed that there's a the density distribution for neutral hydrogen.
Yes.
So why this distribution is motivated from the dark matter halo distribution?
No, the distribution is not motivated, only the form of the concentration parameter is motivated. So people found that when they use such a form to model damped Lyman alpha system, which is what I showed in the next slide, the concentration parameter, the way the hydrogen sets the scale for the gas, evolves very similarly to the dark matter itself. So all this is all hydrogen parameters, but just the way that it evolves with mass and redshift is inherited from dark matter.
So it's basically observationally verified, right?
Yeah, this is something people found since 2010 and 14. So we just brought it together into a comprehensive framework.
Okay, thank you.
Yeah. Okay, so it is now interesting to note that when you take this set of data as well as the parameterized halo model, you can actually get more precise constraints on these 5 parameters than we would naively expect. And it turned out to be much better than we thought at first glance. We found that though the constraints are coming from this very diverse set of observations like galaxy surveys, intensity mapping, and DLA sort observations, we are able to get quite good constraints on all these parameters, and also their uncertainties with the help of a Markov chain Monte Carlo framework. So this is interesting because it showed us that this framework and its evolution, which was also physically motivated, fits the data all over this redshift range of from 0 to 5 in the damped Lyman alpha system. So for example, these observations are just like luminosity functions. These are probabilities of different column densities occurring in the neutral gas. This is an observation coming from that intensity mapping, which I told you, an integrated emission of radiation. What is more interesting is what is shown on the right-hand side of this line. These are some few observations which were never directly fitted to the Markov chain Monte Carlo, but they just fit out of the box. Like for example, here I'm showing you some observations of the surface density. So this is actually one of the prime constraints on this concentration parameter and its evolution. The error bars on this are really high, so it was amazing that it fitted as well as it did. It also fits the covering fraction of DLEs, which is another constraint on how the cutoff and the profile are working together. So that was very interesting and gave us more confidence in the fact that it's fitting observations which were not modeled. And also, it had some very salient features, some very interesting features. The first one is that this is manifestly characterized by a non-unity slope. So, for example, when I talked to you about the H1 mass to halo mass, and this parameter called beta, which is kind of telling you the deviation from proportionality. This line shows you like when the H1 mass would be proportional, whereas you see that the best fit is quite, quite far from it, and it is manifestly a non-unity slope. And the profile also is exponential, and that is also quite physically motivated, and it turns out to be the case. What is interesting is that the scale radius, the typical radius of this neutral hydrogen, is like what we would expect, something a few 10 kpc, which is typically a galactic scale. And so this also worked out to expectations. Interestingly, this is not just all statistics and fitting and Markov chain Monte Carlo, but it also gave us a lot of very interesting physical insights. So the first one is that each of these parameters told a kind of story.
Hamsa, we have a hand up
Yeah.
by Kandu.
Hi, Hamsa.
Hi.
I was wondering why there is such a sharp drop at z equal to 0 at low masses. In the previous plot, which
Yeah. Okay, this essentially happens because at z is equal to 0, we have the mass function of the neutral hydrogen, and we don't have constraint on it in like, so that function essentially constrains the low mass end pretty well. So it makes it, if at higher masses, we only had the damp Lyman alpha constraint. So those were all in the profile. So concentration parameter as well as the mass function sort of came together here, and it sort of made the 1 plus z dependence crunch up these masses. So it's essentially the virial velocity at work here. So 1 plus z raised to 1/2 kind of widened the gap a bit.
So you're saying it's not physical or what?
Oh no, it is absolutely, it is physical based on all the data which we have. It's physical because the virial velocity cutoff essentially introduced this sharp drop at redshift of 0. And we don't have mass function. I mean, with SK, we will have them. So we will know if the DLA and like the mass function are consistent even at high masses. So at right now, we only have that at redshift of 0.
Okay, we can discuss later. Thanks.
Yeah, so the first one is called alpha, and alpha is essentially the normalization of this function at redshift of essentially at all redshift, because alpha, you can see that there is no evolution with redshift. So what alpha came out to be was about 10%, and this 10% was very consistent with most of the simulations and observations, which found that cold gas is roughly between 10 to 20%, which is both neutral hydrogen as well as molecular hydrogen. And interestingly, as I said, this alpha is not evolving with redshift. This was not something which happened by design. We did allow it to vary, but it stubbornly refused to incorporate any dependence with redshift from the Markov chain Monte Carlo. This actually signifies something very physical. We found that there have been works all the way since about a decade ago, which said that the accretion of the fresh neutral hydrogen kind of balanced the consumption by star formation. So we had this kind of circular, balance in the galaxies, which led to something like a non-evolution. So alpha essentially came out of that. The other parameter, which is beta, or the slope, has an interesting history. It was actually connected to several approaches people were doing in the past, which were to model these systems both at low and at high redshifts. And what we found is that you had models for 21 centimeter based sort of observations, which were very low redshift, and for the higher redshift, damped Lyman alpha based observations. And what is interesting is that these models are quite different in nature. They are functionally very different. We did one study where we looked at whether we can just at face value combine the previous modeling approaches and ask what kind of constraint would that would that give in the light of the data. What was found is that it actually fits almost all the observations pretty well, but where it does not fit is precisely in the neutral hydrogen mass function, the H1 halo mass. And this happens because it is sort of having a kind of over prediction at the high mass end. And this is related to the fact that all the approaches had the proportionality. They had a beta which was 0. And what the MCMC taught us, so to speak, is that if you have a beta which is like smaller, then you would have a non-unity slope. And this is very much constrained by the neutral hydrogen mass function. And it's also something which is related to a very physical phenomenon, the quenching or the feedback which occurs in these galaxies. And this again has been the subject of several simulations. So the third parameter, which I called as VC0, is something, as I said, related to a scale, a kind of boundary. And this is also a lower cutoff. So this tells you that what kind of systems the neutral hydrogen is preferentially suppressed as compared to the systems where more of the galaxies are able to host neutral hydrogen. The number you get for this is something like 36.3, and at face value this is not a very intuitive number, but what really makes it interesting is that if you look at analysis stretching back to 86 and even before that, you have like a bunch of studies which showed us that there is a photoionization which suppresses the formation of dwarf galaxies. And these dwarf galaxies are suppressed typically. If you take the constraints on ultraviolet background, you can do an analytical calculation, which makes this come out to about 37. So it's amazing that a study in 2017-18 confirmed this to so much of accuracy and showed us that there's a suppression going on. And indeed, it is happening around this kind of kilometer per second, like 36. So not only that you can get astrophysical insights, I wanted to spend some time showing you that you can also get some very interesting cosmology from combining the results of the halo model framework with the observations. The first thing is to look at, for example, the angular power spectrum. So this is how people have been exploring for the CMB. You have these power spectra in different redshift bins and the CL. So the way you would do this is to take the existing cosmological parameters and importantly, add in the astrophysics with realistic priors. And these realistic priors come from using the halo model framework. So you can, I mean, it's just a coincidence that the kind of best fitting astrophysics happens to be also 5 in number. That was not a plan, but it sort of just nicely symmetrizes with the cosmology in the case of neutral hydrogen. And when you do this, you can convey, you can constrain the degradation of these cosmological parameters with and without the presence of astrophysics. So these are just some indicative examples. Don't worry about the actual numbers on the y-axis because these are a function of foregrounds and different physics and so on. What this allows you to do is that in cosmological parameters, you can quantify what kind of degradation the astrophysics will induce for you, and also tell you how much this degradation is alleviated by the redshift interval which an experiment is sensitive to. So for example, in the case of experiments such as CHIME and SKA, you will have a large redshift interval. And what we found is for most of the experiments, the degradation is almost completely cancelled by the fact that you are probing so many Fourier modes and you have access to a large redshift range. this is all about precision. So this is just like how precise you can get the errors in these astrophysics and cosmological parameters. But there's also some other things you can do. That one of the main things is when you have the 21 centimeter intensity mapping, especially if you're going to high redshifts, then one of the important issues is that of foregrounds. So foregrounds are almost about 100,000 times more bright than the signal. And one way by which we can think about mitigating them is to cross-correlate different maps, like correlate the neutral hydrogen map and a galaxy map, for example. So using the available halo models of galaxies, these have been studied extremely well for quite a few decades now. So using that in combination with the neutral hydrogen halo model allows you to sort of write down expressions for cross correlations of these two data sets. And a typical example is to look at, like, for example, the CHIME and DESI. So CHIME is a telescope in Canada, DESI is in Kitt Peak, and these are going to start off by the next year or so in cosmology. And what we find is that if we have a forecast for cross-correlating them, then you get very good constraints on the cosmology as well as the astrophysics, because the two maps sort of combine to decrease the noise and improve the constraint. These are even comparable to those from the SK1 auto, which is an unfair comparison, of course, because by the time SK is in, you are going to have the LSST, which is going to give you a very good cross-correlation probe. But it just shows you that cross-correlations are able to get you much better constraints than the auto. And just not just the standard cosmology, we could even go beyond the lambda CDM model, which is the most exciting with the intensity mapping. So to do this, as I said, thus far I talked about precision, but we can also understand more about the accuracy by using these priors in a statistical framework. So the way we do this is that you have these mechanism in place to think about how certain parameter shift can induce bias in the remaining parameters using nested likelihood and such other techniques. So when you do that, you essentially take, for example, the astrophysical parameters, the kind of errors which they have, and ask what kind of deviation, what kind of bias would they induce in the cosmological ones. Interestingly, this allows you not just to do so for the standard cosmology, but also for example, the primordial non-Gaussianity parameter. So primordial non-Gaussianity is what would make CMB maps which look like this turn into something like this if it was a very large primordial non-Gaussianity. But for reasonable values of deviation, people have shown that a primordial non-Gaussianity induces something like a sort of increase or decrease in the bias of the tracer, which is tracing the large-scale structure, the dark matter halo. And interestingly, if you have reasonable uncertainty in the astrophysics of the H1, then the primordial non-Gaussianity constraint is gratifyingly very close to 1 sigma, so that it's negligibly affected by the astrophysical uncertainty, which was a very interesting finding because it is one of the strongest science cases for these experiments. We can also look at, for example, some deviations from the standard dark matter. There are some axion-like models. So this is a study led by a student, Jurek Bauer and collaborators at Göttingen. And in this, they found that you have a lot of promise for SKA to distinguish between the models of dark matter, which are made up of axions. So we can do various of these fundamental physics with the neutral hydrogen, but also we can do this with other lines, which I thought I'll spend one slide on. And I mentioned that, for example, the carbon monoxide and the C+, which is the ionized carbon, are excellent tracers of the slightly smaller scales, but also over large volumes. So in these two papers, I was looking essentially at how we can use the same kind of halo model techniques to look at the evolution of carbon monoxide and the C+ ionized carbon across a range of redshifts. Interestingly, it was found that using all the data which we have combined in this kind of framework, you can actually predict very good constraints for signal to noise ratios for experiments which are detecting the carbon C plus in intensity mapping, all the way out to almost the epoch of reionization. So this is very exciting, and that is what now leads very naturally to giving us insights into the first galaxies, into the first galaxies hosting these elements. So when you come to the first galaxies in this framework, we also looked a bit at what their properties are in terms of the central supermassive black holes. So using a similar approach as what I had described for you for the neutral hydrogen, people have modeled the properties of these central supermassive black holes in the help of a halo model framework. So these are certain studies which did that. And what you'll find, which is very interesting, is that the way this black hole mass to halo mass evolves is very different from the way the neutral hydrogen mass evolves. And also, it was very different from the way the stellar mass evolves. The stellar to halo is quite, quite constant. It doesn't evolve too much across various redshifts. But the black hole mass is seen to grow very, very fast. So if you take this kind of picture, then it leads to actually several insights about even galaxies around the reionization and closer to cosmic dawn epochs. One prime example is in how you can use these same systems in their gravitational wave signatures, detectable with the forthcoming LISA observatory. So as we know, LISA is probably going to be out in the 2030s or so, and it's a space-borne mission. It's especially sensitive to the extreme mass ratio in spirals and massive black holes, which are between the range of 10 to the 4 to 10 to the 7 solar masses. Forecasts for it have been done for from quite a long time ago. And very recently, there was an interesting paper in the Astro 2020 Science Cases by Monica Colby and other collaborators, where they looked at, for example, you can see on this slide the different time scales we've been interested in, like the highest redshift galaxy detected so far, the highest redshift quasar, highest redshift GRB, and also the period of cosmic dawn. But this time you can also see here the signal to noise of the gravitational wave signature detectable by LISA. For example, for merging black holes of masses of this kind of range, you may be able to get it even to almost the period of cosmic dawn. So in order to think about how to incorporate this into a consistent framework, we looked at how the merger rates of dark matter halos would work out with the help of the black hole to halo mass relation, which I described previously. So in the very recent studies, people have parameterized these merger rates in terms of the dark matter mass and their ratio of masses. And by using the framework which I described for how the black hole mass is connected to halo mass, you can actually parameterize the main observables involved as what you may call known and unknown parameters. So what the difference between known and unknown is that those parameters are well constrained by the forecasted, at least by the LISA observatory for different survey areas and survey timescales, etc. But these ones are more astrophysical in nature. So for example, these two are the halo model parameters for the black hole to halo, and this one is something like an occupation. What we found is, just like in the case of neutral hydrogen, we can use a Fisher matrix formalism. Here we can modify the Fisher matrix formalism by using the information which we already have from forecasts of the known parameters. So people have done this, like getting the errors on like the masses and the mass ratios from different kinds of LISA surveys. And interestingly, if we modify the standard Fisher matrix technique by using a tabulation of the known parameters and their errors, then it allows us to recover optimistic or pessimistic constraints on the astrophysics itself. So this is quite interesting, and it offers a direct view into the properties like the halo model of the black hole to halo mass and their occupation at high redshifts by using all the information in LISA surveys. So this really shows the power of the multi-messenger technique, which is probably going to be our go-to technique for recovering information right from the earliest sources of reionization and all the way until cosmic dawn. So the approach seems to be just that a cross correlation would yield a lot of results, right from cross correlating the gravitational wave signatures with those of 21 centimeter and from the galaxy surveys, and importantly sub-millimeter. So already it shows a lot of promise. And in this paper, which is a review article we co-edited for the Square Kilometer Array collaboration, it was quite obvious that there are some interesting fundamental physics which are possible to be constrained. And these include, for example, whether the fine structure constant evolves with time, of which there have been a lot of studies in the literature. And now, with the help of cross correlation, we can also explore primordial non-Gaussianity at the epoch of cosmic dawn. The axion and other kinds of milli-charged dark matter can be also kind of constrained at these epochs. And there are a lot more exciting fundamental physics which we can do, especially given that this is the largest number of modes we are ever going to be able to access. So that's about it. So let me quickly summarize by telling you that when we do baryonic surveys, which are probably going to be the surveys of the future, closing the gap between the local universe and the CMB, we would need to take care of this astrophysical systematic in a very sort of distinguishable way. And this is something which a halo model, a data-driven framework, does quite efficiently for you. And it allows you not just to explore the impact of the astrophysics on the precision and accuracy of the cosmological forecasts you get, the kind of degradation which you might get, but it also allows you to handle the cross correlations with large galaxy surveys which are going to come up in the future. This is something which leads you to insights, for example, when we use sub-millimeter intensity mapping right up to the epoch of reionization. And importantly, can give you insights into the properties of the first black holes, which is indeed one of the outstanding questions in cosmology and astrophysics. This is something which can also very, in the future, with the help of large surveys, even constrain fundamental physics beyond the lambda CDM model by using the data between the cosmic dawn and the present day. So I think it's a very exciting time for future surveys in cosmology and astrophysics. So thanks a lot. Stop here.
Thanks, Hamza, for this really wide-ranging talk and just illustrating the power of using multiple observational channels in tandem. I really enjoyed the talk. Okay, so the floor is now open for questions. And there is a question by Prajwal. Prajwal, please unmute and...
Yeah, thanks. Hi, Hamsa, lovely talk. So I had two questions. One is you mentioned that SK data could potentially rule out axion-based dark matter models, and it would be nice if you could elaborate a bit on that. And my second question was, you said that there was evidence for black hole masses. I guess you meant supermassive black hole masses evolved stronger than the stellar mass. How would that manifest in the supermassive black hole M sigma scaling relationships?
Okay, just to answer the second question first, this is derived from the M sigma. It is just because the VC raised to the power of something like 4 to 5 is the one which the VC and the sigma, they are almost similar for the disk-like scenarios. So if you just
Okay.
take the velocity evolving with redshift, this is the kind of constraint you get. So essentially, it comes straight out of that.
Okay.
The first, yeah. So then about the axion dark matter, it is actually not that it, I'm not sure if it can actually rule out. What was found here is that for a particular kind of the ultra light axion ULA models, there is a certain mass range of the axion at which the SK can place constraints, like what kind of mass range, what kind of abundance. This is what can be done at sub-percent level. I'm not sure if it can actually rule out models. Possibly it can, but what we studied here was more on the different mass ranges of axions.
Okay, thank you very much.
Thanks a lot for the question.
Okay, if other people have any more questions, please feel free to raise your hands while I ask a question. So when you say you're cross-correlating these intensity maps with, let's say, galaxy surveys, what exactly are you doing in practice? I mean, I know this might be a basic question, but yeah, it'd be nice if you could answer this.
Yeah, let me just come to that. Yeah. Okay, so the way one does this is, well, there are several ways, but I can just tell you one of the ways people are advocating in the literature. Essentially, you are using two maps whose foreground or the kind of systematic, which you expect, are quite different. You don't really expect that the 21 centimeter or carbon monoxide or galaxy have same foreground. It can happen, but in a good approximation, it doesn't happen. That means that when you average out, when you cross these two maps, the foreground component goes away. So you are then just left with the signal. Of course, when you do it for the maps like the carbon monoxide and so on, when you actually want to isolate one of the component, you will need to use, say, two cross correlations. So carbon monoxide is quite interesting in that sense. One of the things we do with the COMAP collaboration, which is led out of Caltech and which many of us are involved in, is that you take two bands which are separated by an integral multiple, because carbon monoxide, as you know, has these transitions which are integral multiples of states, j into j plus 1 kind. And this is exactly the kind of difference in the redshift. So 1 plus z is also an algebraic multiple. This is nice because then when you cross-correlate the 1, 0 line and the 2, 1 line, and that allows you to isolate a component of the reionization signal. So essentially, it's a way to hopefully mitigate the effect of systematics and foregrounds. At the same time, you get better constraints on several of the astrophysical parameters.
Okay, I think I understand it better now. So I don't see any more questions, but so I'll ask one question. Could you go to the slide where you show these 2D histogram plots or 2D corner plots in the gravitational wave section of your talk, the LISA section?
Yeah.
I think my connection is a bit bad, so the things are moving slow for me. Yeah, so okay, wow, I can't see this. Yeah, anyway, so basically, you are considering. So what is the system in LISA you're considering here? So is it an extreme mass ratio and spiral with some mass ratio?
No, these are, well, this plot is not our paper. This is the plot which we used to get an idea of the deltas in these different parameters. So this is a plot from Lang and Hume. So what they did is they explored two different scenarios with and without spin precession. That's why there are two different kinds of lines. And these are essentially the kind of constraint you will get depending on the, so you see the masses go from something like 10 to the 5, 10 to the 6. And depending on the kind of initial masses of the two systems, you will get different constraints on the errors you expect on these masses. I think this uses 5-year LISA survey, something like that. And depending, of course, we scale them to the kind of survey which we are interested in, and their errors become proportionally lower. So this is just a way to parameterize. And here is, for example, the cosmological luminosity distance, which will give you a delta Z by Z, assuming a standard cosmology. Does it make sense? This is, yeah.
No, actually, my question was about the kind of systems that you are using. So what are those kind of systems?
Similar systems.
Okay.
So the way we would do this, like I said, when there is more information on these known parameters, what you do is actually just what you would do for a standard Fisher matrix. But interestingly, the x-axis becomes three-dimensional in that sense, if you get it. So if you see like the mass and the Q and the Z, these are three parameters, and all of these are like the independent variables because we have constraint on all of them. So you can take masses. So this is, for example, the mass range. This is like the Q range. And so it's like that. So that's why you can essentially use the uncertainty which people expect on each of these to derive the best constraints on the parameters which you care about in this scenario, when you care about, like, say, the astrophysics of the black hole. And this is generalized.
Right. So do you use some kind of merger rate approximation for this?
Absolutely. So merger rate is coming from that's coming back to Prajwal's question, and also coming back to what I was mentioning, the halo model. You would use the merger rate because you would use like the underlying dark matter merger rate, and that gives you a very natural way to place the halo model for the black holes into it. So the black hole to halo mass has an analytical expression. I haven't written it out here, but it's essentially something which goes like the circular velocity. It's coming from that. So you can write down in terms of redshift. That is when you can quite cleanly separate the astrophysics again from the cosmology, because you will just put that into this merger rate. And thus you will derive the resultant merger rate for the black hole masses. And that expression will contain all these Sorry.
Correct. Yeah, now I understand. So how does this merger rate translate to a per year merger rate in LISA?
Right.
So how many black holes per year?
Yeah, so depending on this merger rate, you will just use the 1 plus z kind of expression, and you will get it will of course depend on all these different parameters. So you can draw curves. For example, here you have per giga year. These are the kind of merger rate for, let's say, for example, for different redshifts. So between redshifts of 5 and 6, for example, and here you'll have about 10 maybe per giga year of dark matter.
Okay, thanks.
And therefore a similar number in black hole. Yeah.
Right, yeah, I understand. Thank you, thanks so much. Are there any other questions? Okay, I think Mukesh has a question.
Yeah, wonderful talk. I have a very basic question. So in the starting of your presentation, you talked about the completion of this reionization era, right?
Yes.
So reionization, if I understand it correctly, that is something has to do with the reionization of the neutral hydrogen, right? After the formation of first stars. So as I understand that from a talk, that there are galaxies which are filled with this neutral hydrogen gas even now, and it is being ionized. So there might be ionization happening right now also, right?
Indeed, yes, absolutely.
Then why do we say that that ionization has been completed? Can't we say that it is happening today also?
Okay, so that really depends on what you, how accurate you want to be numerically. And so the reason, the main thing which happened and now has completed is what is called the overlap of ionized bubbles. So the way it worked is the following. You had sources which switched on in the early universe, and each of them produced bubbles, which are essentially the ionized regions around them. So originally, these bubbles were small in size because they were only covering, remember that everything was neutral, and these bubbles only covered that much of area where what is known as the front was able to reach, where at the end of that area, there was a balance between ionization and recombination. But as we had brought more and more sources into the game, all of these started forming their own ionized bubbles. And there came a time when these bubbles had a full overlap. So until that full overlap, we would be completely justified in saying reionization is happening. However, once that overlap is complete, people like to say that reionization is complete. Although, as we discussed, there is of course some ionization and so on going on, but the real crucial point is this complete overlap. This is believed to have coincided this is believed to have happened during a time when around, let's say, redshift of 6 or maybe a little bit after that. And what is very important is that after that, you had only about 1 in 100,000 or so of the neutral, of the hydrogen in the neutral form. And most of that was locked inside the galaxy, as we found. Does that make sense? So ionization, the reionization was indeed happening, let's say from the time when the first sources switched on until these bubbles were forming and so on. But it's said to be complete when complete overlap has occurred.
I see. Thank you very much.
Yeah, I think there's one more question. Sorry, I put your hand down thinking it was from before. So please.
Is that for me?
Yes, yes.
Okay. Yeah, Hamsa, so I was wondering, is it possible that with this analysis, you can arrive at constraints on direct collapse black hole seeds? I mean, stellar black holes are sort of inevitable. Very high mass stellar black holes are sort of inevitable, but don't fit the bill to make supermassive black holes early enough. And so we do need direct collapse black hole seeds. And I was wondering if your analysis can say something about that.
Yeah, I would probably say here potentially yes. At this point, we focused on three quite sort of key parameters in the black hole formation and mass function, two of which are related to the way the black hole mass to halo mass is constrained. And the third one is called occupation, which is just the occupation FBH of the black holes inside the dark matter halos. I think that the direct collapse will also provide constraint on these parameters as well as the parameter which relates the black hole to halo mass. So it's definitely an interesting thing to constrain.
Okay, thank you.
Okay, thank you for your questions. Are there any other questions? Last call for questions, and I don't particularly see any in the chat or in the participants list. So I guess we should end the talk here. And thank you so much, Hamsa, for speaking once again and accepting our invitation. It was really a nice talk. And we hope to see you in the future sometime in person.
Well, thanks a lot, Aditya, and thanks to everyone. I had a great time and look forward to seeing you in person sometime soon.
Okay, bye-bye.
Bye.